Alright, flow measurement in pipes and ducts, course content introduction. Alright, this is course. It's about measuring the flow rate of fluid flowing under pressure is closed in a closed conduity. Closed conduity is often circular but also may be square, rectangular, such as heating duct, any other shape. The other major category of flow is open channel flow, which is a flow of liquid through free surface to open atmosphere pressure. Measurement of flow rate of the flowing fluid. Fluid flowing under the pressure is carried out with a variety of purposes, such as billing of the water supply, homes and businesses, for mining or process control. A wide variety of industrial processes involve the flow of flowing fluid. Several categories of pipe flow measurement devices described and discussed include some associated calculation. Shows pressure taps, Pete 1 and 2, diameter 1 and 2, and quantity, orifice meter. 2. Learning objectives. At the conclusion of this course, the student will be able to calculate flow rate with the measured pressure difference, fluid properties, meter parameters, using the provided equations of the venturi orifice of flow nozzle meters, be able to determine the type of the ISO standard pressure tap locations are being used given the orifice meter, be able to calculate orifice coefficient with the specified orifice pipe, the diameters, pressure type, location, fluid operations. Be able to estimate the density of the specified gas, specified temperature or pressure using the ideal gas equation. Be able to calculate the velocity of fluid given pit pipe, pitot, tube reading, and fluid density. Notice general configuration, principle or operation, roto, and positive displacement, electromagnetic target, turbine, vortex, ultrasonic meters. No recommended application to each of the type of the flow meter discussed in this course. Be able to familiarize with the general character of the type of the flow meters discussed in this course, summarized in Table 2 of the course content. 3. Type of the pipe flow measurement device. The type of the pipe flow measuring devices discussed in this course are differential pressure flow meters, venturi meter, orifice meter, flow nozzle meters, variable velocity flow meters, pitted and pitted stakes, tubes, variable area flow meters, rotometers. 5. The displacement flow meters, miscellaneous electromagnetic flow meters, target flow meters, turbine flow meters, vortex flow meters, ultrasonic flow meters. 4. Differential pressure flow meters. The type of the commonly used for the differential pressure for the flow meter, for the orifice vent meter, for the venturi meter, for the flow nozzle meter, for the 3 all function, for the introduce, for the reduce, the R through the fluid must flow of the decrease in the area cut, for the increase of velocity, for the turn, the result of the decrease of the pressure, for the flow meter, for the pressure difference between the point of maximum velocity and minimum pressure of the undistributed for the upstream flow, with is measured by can be correlated with the flow rate. Using principle of conservation of the mass of the continuing operation equal for the conservation energy equation without friction. The Bernoulli equation. Following the equation derived with the ideal flow between the upstream undistributed flow subscript 1 downstream condition where flow area is constricted subscript 2. So you have the ideal flow rate in neglecting viscosity and other friction effects and cubic feet or seconds is equal to constricted cross-sectional area normal flow rate 2 feet squared squared by the under the square root of 2 upstream undistributed pipe flow pounds per feet minus the pressure in pipe where it flows constricted with the area A2 the constricted cross-sectional area normal flow by pound per feet squared over P minus 1 minus B, which is diameter 1 divided by diameter 2 divided by diameter 1 at A2 pipe diameter. P is the fluid density slugs fit cubed. Discharge coefficient typical to put in the equation account with the friction and any other non-ideal figure factors given the following general equation for the differential pressure meters. Q is the flow rate of the pipe of the meter for the feet per second. C of the discharge coefficient is dimensionless. A is all other parameters defined above. A2 with the constricted cross-sectional area nominal flow minus P. Upstream pressure in pipe minus pipe pressure where flow area is constricted. Divided by fluid density in slugs times 1 minus B4, which would be the diameter 2 minus the diameter 1 Each of the three differential pressure flow meters will begin with a considerable separately. Ventral meter. Fluid enters the ventral meter converging with a cross of the angle of 15 to 20 degrees, with it thus pass through the throat with a minimum cross-sectional area with the maximum velocity, minimum pressure from the meter. Flow to slows down through the divergent coming to the angle of 5 to 7. The transition back of the full pipe diameter. Failure 1 show the shape of the typical ventral meter. Parameter defined above the supply with the type of the meter. Diameter 2 is of the throat. P2 is the pressure at the throat, D1 and DP1 over the pipe before entering the conversion portion of the meter. Alright, figure 1 shows ventral meter parameters. Q, P1, P2, diameter 1, diameter 2. Due to the smooth transition of throat with a gradual transition back to the full pipe with the diameter of the head loft of the ventral meter was quite low with the discharge coefficient is quite high. The ventral meter with the discharge coefficient, typically called the ventral coefficient, or received with an underscore V, subscript V, or is known as ventral coefficient, given the following equation: ventral meter Q quantity is equal to the ventral coefficient times the original equation of your ideal flow between upstream and downstream. Alright, the value of the ventral coefficient, typical range from 0.95 to nearly 1. ISO 5167 sees reference to for the scores. Coefficient ventral is given with a 0.995 cast iron machine ventral meters or in 0.985 of the welded sheet metal ventral meters meeting the ISO specifications, all for the Reynolds number to between 2 times 10 to the 5th and 10 to 6. Information ventral coefficients will typically be provided with the ventral meter manufacturers. Our example, the one water at 50 degrees Fahrenheit with the flowing through the ventral meter within 2 inches of the throat diameter with a 4-inch diameter pipe. Per manufacturer coefficient ventral with a 0.99 for the meter under the flow condition of the flow rate through the meter is pressure differential. Pressure 1 minus pressure 2 with a measure of 8 inches of the HG. Solution. The density of the water temperature ranging from 32 degrees Fahrenheit to 70 degrees Fahrenheit with is 1.94 slugs foot cubed. 3 significant figures. So the value will be used. The area squared. Area 2 is equal to the pi diameter 2 to the second and divided by 4 equal to pi times 2 to the 12th divided times the second divided by 4 equal to 0.02182 feet squared. And then B is equal to 2 divided by 4 equal to 0.5 converging pressure differential pound per square foot. Pressure 1 minus pressure 2, 8 in HG, 70.73 pounds in foot in the HG. 565.8 pounds of feet squared, substituting all the values of the equation 3. And it shows your calculations. Orifice meter for the simple for the 3 differential pressure meters, flow meter for the consistent circular plate with a hole in the middle, typically held in the plate between pipe flanges, shown in Figure 2. Figure 2 shows the orifice pipe diameters. Quantity of the different diameter 1, diameter 2, line 1, line 2, pressure 1, pressure 2, taps. Orifice meter with the diameter, orifice for D is U for the itself, and the diameter 2, given that the area 2 is equal to A to 0. The discharge coefficient, typically called the orifice coefficient given with the following equation for an orifice meter. The orifice is equal to the same equation. This time A is in subscript 0. The orifice, the preferred location of the pressure type of the orifice meter have undergone changes over the time. Previously, downstream pressure tap preferential located with the ventral contracta. Minimum jet air with the curve of the downstream of the orifice plate is shown in Figure 2. Ventral contracta tap of the tap location depending on the orifice hole size. Link between the tap location and the orifice size made with a different size change of the orifice plate with a different hole plate size within A given the meter with the ordered range of measurement in 1991 ISO 5167. International standard came out with which of 3 types of differential pressure taps have been identified with the orifice meters. Those shown in Figure 3 below, and ISO 5167. The addition of the pressure tap of the orifice plate with its specified the fixed distance of the function over the pipe diameter rather than the orifice diameter is shown in Figure 3. ISO 5167, the equation for the orifice coefficient given the function of the B Reynolds number line 1 and line 2 for the distance of the pressure tap from the orifice plate is shown in Figure 2 and 3. equation given in the next paragraph can be used with the orifice meter with any of the three standard pressure for the tap configurations. Figure 3 shows the ISO standard orifice pressure tap locations. Corner taps, the diameter minus diameter and a half taps, and flange taps. Okay? The ISO 5167 equation with the coefficient orifice also available the reference of the number 3 with the core of the U.S. Department Interior Bureau Reclamation Bureau measured measurements coefficient is equal to a large equation where coefficient efficiency is defined in the equation dimensionless. Line 1, pressure tap distance of upstream face of the plate in inches. Line 2, pressure tap distance face of the plate in inches. Downstream, D is pipe diameter inches. B is the ratio orifice diameter to the pipe diameter. Orifice diameter to the pipe diameter dimensionless. RE Reynolds number to dV and minus V is equal to dVp is divided by U. Dimensionless in dimensionless D is in feet. V average velocity in fluid of the pipe is equal to quantity divided by pi times the diameter squared divided by 4 in feet and second diameter in feet. V kinetic viscosity of flowing fluid v foot in second. P diameter density of the flowing fluid in slugs cubed. U dynamic viscosity fluid flow in pounds per square fair sheet. Alright, shown figure 3, L1 and L1 is equal to L2 is equal to 0. Corner taps L1 equal to L2 and 1 inch of the flange taps L and L equal to the diameter and L2 is equal to the diameter divided by 2. Therefore, D minus divided by 2 taps. Equation 5 is not intended for the use of any of the other arbitrary values of the line 1 and line 2. Minimum allowable value of the Reynolds number to use with equation 5 is valve flange taps and D minus D divided by 2. The Reynolds number must be greater than 1,206 B squared D. Diameter of the corner tap is Reynolds number with greater than 10,000. If the B is your ratio or if the pipe diameter is greater than 0.45, Reynolds number must be greater than 5,000, or if the pipe diameter ratio is less than 0.45. Fluids of the kinetic viscosity and the density of the fluids, slugs, and the dynamic viscosity flowing rate pounds per second needed in order to use the equation tables to graph the value of the velocity, the density, and the dynamic viscosity of the water and other fluids over the range of temperatures available to many handbooks, fluid mechanics, thermodynamic textbooks, as for example the reference number 1 of the course table 1 show the density viscosity of the water temperature of 32 degrees to 70 degrees Fahrenheit. Show 32 degrees, density slug 194, and then viscosity of 3.732, 10 to the 5th, 12 and 19 viscosities. Alright, for example, the Reynolds number of water of 50 degrees found with the U035 with the cubic feet per square second through a 4-inch pipe diameter. So the calculation volume of the block, and then equation 3. Use equation 5 to calculate the orifice coefficient of the orifice diameter 0.8, 1.6, 2.0, 2.4, 2.8 inches. Each 4-inch diameter pipe with a RE, a Reynolds number of 10 to the 5th for each of the standard pressure tap configurations. 1 D minus D is divided by 2 for the taps, 2 flange taps, and 3 corner taps. Alright, solution make all these equations. You'd be the handy using equation would be radius tedious, but once with equation set up with the Excel spreadsheet with the repetitive calculation, you've easily done following the copy of the Excel spreadsheet solution of the problem. That shows your D and minus D and a half taps, flange taps, corner taps. Note the orifice coefficient of between 0.597 and 0.63. All for all 3 pressure tap configuration. Reynolds number to 10.5. The orifice pipe diameter 0.2 to 0.7. The ratio. Large value Reynolds number of the orifice coefficient will stay within the range. Smaller value with the Reynolds number orifice coefficient will get smaller, somewhat larger, especially with the higher values of pipe ratio. Example 4. Water at 50 degrees and flowing over the orifice meter of the flange tab with a 2-inch throat diameter, 4-inch diameter pipe. The flow rate through the meter in the pressure referential. Pressure 1 minus pressure 2 is measured in 8 inches of the HG. Assume that the Reynolds number is approximately 10.5 in order to get started. Then from the solution E through example 3, your pipe ratio 0.5, coefficient 0.60579. For the table of the density of the water, 50 degrees, 1.94 slugs foot, area square of the pi, minus D to the third, D to the second diameter to the second power divided by 4, and then you get 0.2182 feet squared, and ratio 2 to 4, 0.5 converting pressure differential. Pounds to feet, pressure 1 minus pressure 2 is 70.73 pounds per feet, or equal to 565.8 pounds a feet. Substituting all these values in the equation. Check out the Reynolds number value. V is equal to the quantity divided by area. Is equal to 4.152 feet squared. Reynolds number to dVd divided by velocity divided d by value to v by velocity. 9.836 10 to the 4. The value is close enough to 10 to 5, so the value is u. The coefficient is okay. Flow nozzle meter. The flow nozzle meter is simpler, less expensive than a venturi meter, but not quite as simple as the orifice meter, but consists of the relative short nozzle, typical held in place between the pipe flanges, shown in Figure 4. Figure 4 shows flow meter parameters: quantity, diameter 1, diameter 2, pressure 1, pressure 2. A flow nozzle meter with the exact diameter of pressure nozzle with the diameter is u with the given of the area 2 with the area A is equal to area N. The distance coefficient, typically called the nozzle coefficient. Nozzle coefficient given the following equation: flow nozzle meter. Original quantity equation, but with the coefficient equal coefficients times the area. Do some of the smoother contracting flow nozzle coefficient, significantly higher orifice efficiency. They're not higher than highest venturi coefficient. Flow nozzle efficiency typically range from 0.94 to 0.994. Several different standards for flow nozzle design. Information on pressure tap placement configuration should be provided with the meter manufacturer. For Excel spreadsheet, make orifice venturi meter calculation. See engineeringexceltemplates.com. Alright, 5. Velocity flow meters, pitted static tubes. Pitted tubes are also called pitted static tube, with an inexpensive but convenient way of the measure velocity of the point of fluid. They are used widely in airflow pressure measurement and ventilation. Have the application definition for the three types of pressure measurement of the given below, but the understanding that helps understand the pitted tube equation: solid pressure, dynamic pressure, total pressure defined below and illustrated in Figure 5. Static pressure, fluid pressure relative to the surrounding atmospheric pressure measured for the flat opening, which is parallel with fluid flow, as shown in Figure first YouTube manometer from Figure 5. Stagnation pressure is the fluid pressure relative to the surrounding atmospheric pressure measured for the flat opening perpendicular to and facing with the direction of fluid flow, shown with the second YouTube manometer in Figure 5. This is also sometimes called total pressure. Dynamic pressure of fluid pressure relative to the static pressure measured through a flat opening perpendicular with a to and facing the direction of fluid flow is shown in the third YouTube manometer Figure 5. This is also sometimes called velocity pressure. It shows airflow, static pressure, stagnatic pressure, and dynamic pressure. Alright, average velocity is equal to V. Density is P. SPWT is Y. Static pressure typically represented by P. Dynamic pressure equal to 1/2 of the P times V to the second. Stagnated pressure represented by the P stags is equal to pressure plus dynamic pressure to height of the measuring point above some of the reference plane shown following equation. Pressure stagnant is equal to the pressure E plus 1 times 2 the density over the average velocity squared times the SP weight times H. Or when the parameter consistent set of units following the P stagnant pressure in pounds of feet. P is the static pressure in pounds of foot. is equal to 1/2 of the density of fluid slugs fitted, times average velocity in feet per second squared plus specifically weighted fluid of a pound to the foot cubed times h, which would be the height above the specified reference plane. For pitted tube measurement, the reference plane can be taken with the height of the pitted tube measurement, so that the h is 0, the height over the above the specified reference plane is 0. Stagnant pressure minus static pressure is equal to dynamic pressure, or P stagnant minus P minus stagnant pressure minus static pressure is equal to half the density fluid times the area velocity second squared. Yeah,